Welcome to all the class 12 science students of Odisha, and here I am here to teach you the chemical kinetics. So, this is the chapter 4 of class 12 in physical chemistry. So, before going to details in the subject, so we must know the broad outlines, the learning outcomes of this chapter. So, we shall go in this way. The introduction will be there, and the rate of chemical reactions, factors influencing reaction rate. So, and there will be next slide showing all these. So, here the slide showing all the outlines of this chapter, and before entering into the chapter in detail. So, I will let you know a very interesting fact that we come across in our home daily. So, every home I think we are having lizards in their walls. So, you will hardly find lizards in winter, and it is easy prey for others. So, lizards are very, in winter. This is because so these animals are their internal temperature is according to the environmental temperatures. Like human beings, we maintain a temperature at 37 degrees centigrade always, but lizards cannot do that. So, due to this, so what happened? So, their muscular actions slow down. In fact, the chemical reactions involved for their motion they slow down, and for which they become slow down and sluggish in winter. So, and rate of reaction, in fact, a very critical area in chemistry. So, in dealing with all science, scientific discoveries, invention and technology, whatever we can say, it is very important. So, let us take an example of a rocket is about to launch. So, in fact, we use fuels in rockets. So, that will be rightly be chosen, so that if the fuel will be slow to be so very much slow to get combustion, so that it will be very difficult to take off the rocket. And similarly, if the combustibility of the fuel is too high, that means the fuel burns very fast. So, what happens that that will lead to an explosion. So, there must be a right balance between choosing a fuel for a rocket. So, similarly we can say that, so all the chemical reactions going around us, even in our metabolic systems or anywhere. So, there must be we must know the speed at which the reactions are going on. So, unless we ascertain the speed, then we cannot say that whether we can get a goal or not, we can achieve something good out of the chemical reactions. So, that is why the topic chemical kinetics is important, and before going in detail into the chapter. So, we must look into the class 11, that is the thermodynamics or thermochemistry that we have been taught. So, where we have been told that a reaction will be spontaneous if the Gibbs free energy function is negative at constant temperature pressure. So, you know this in your class 11 in thermochemistry chapter, this is Gibbs free energy function at constant temperature pressure. If this is negative, this leads to a spontaneous reaction. This leads to spontaneous reaction. So, this is what that you can get, but this thermochemistry is silent regarding that the path followed by the reaction. It only deals with the initial and final states, that means the starting and end point, but it is completely silent or offers no explanation regarding the path followed by the reaction, which is important to control a reaction or for the study of reaction. So, to overcome all these difficulties, so we can we will study the chapter that is called chemical kinetics. So, in chemical kinetics we will answer the questions of the could not been answered by thermochemistry. So, these are the questions that will be answered: how fast a chemical reaction will occur, and what factors govern reaction speed, and what path or the mechanism the reaction follow. So, this is the three major aspects of the chapter chemical kinetics. So, on the basis of these three, we can define the chapter or the subject, the topic to be the branch of physical chemistry that deals with the study of reaction rates, factors influencing the reaction rates, and the path or the mechanism that follow for the completion of the reaction. So, this is how we now will start directly. We have already known the learning outcomes that will going to be taught in this subject. So, we shall start with the rate of a chemical reaction, rate. So, first of all, we must know what we in daily life we use the term rate. So, when you go to the market, you ask the price of the potato or vegetable, fish, whatever you are going to buy. So, the shopkeeper says you it is suppose your potato is being sold at the rate of 20. So, it means 20 kg per 20 rupees per kg. That means and suppose you are all using all mobile phones where your data speed comes in kbps or mbps, so and so. So, where in all these things what we are doing, so there is certain variation with respect to a fixed quantity. So, this is called rate. Suppose a car is moving very fast, we says that it is travelling at 80 kilometer per an hour. So, here the 80 kilometer is the variation or the variant and hour is a fixed quantity with which we measure the variation. So, similarly, in case of when we talk about rate of reaction, we mean that the change in concentration of products or reactants with respect to time. So, that is what we mean the rate of reaction. So, let us first if I will start this rate of reaction as a subject. Suppose this is rate of reaction. So, I will first let me take a hypothetical reaction like this. R stands for the reactants and P stands for the product. So, here the rate or rate of I will simply write rate. It implies the change in concentration of either reactant or product. I can write it. This is rate of disappearance of R. Also, I can write it, that is decrease in concentration of R over a finite time, over a time. Similarly, I can write it, I can tell you rate of appearance, or you can say formation. I can say also rate of appearance of P. P stands for the product, or in equation type I can say increase in concentration of P divided by time. So, this is a general expression of rate of a simple hypothetical reaction. So, where we can say the rate in terms of the rate of decrease or rate of increase. So, that means rate of formation and rate of or rate of decrease in concentration of the reactant. So, but the reaction rate we can in our study you can have two types. This rate can be of two types. So, rate is of two types. One is we call it average or mean rate. We can designate as RAV, and another is instantaneous rate. I can designate as RIN. So, the two types of reaction rates we shall usually come across. So, while dealing with the chemical reactions. So, first we shall go with the average or mean reaction rate. So, R average. So, average means we shall calculate the change of concentrations over a sizable period of time. So, with a definite period of time. So, where we shall call it an average. Suppose it's the same reaction I will take R to P, the R reactants and product. So, R average, so will be, I can write it in this way, that is minus del R by del T, or this is equal to plus del P by del T. So, here you see there is a negative sign here. So, negative sign actually indicates the fall of concentration of the reactant with time, and the positive sign indicates here the rise of concentration of product with time. So, you can better understand this using a graph here. So, if we plot concentration versus time, here is a concentration in y axis, time in this. So, this is going, this is the fall of concentration. Suppose this represents at this time, this is a time, suppose T1, this represents the concentration R at a T1, and this is time T2 at a higher time. That means the reaction has proceeded some certain time, this R T2. So, if I will expand this term for average rate. So, from the graph, so I can write it like this, R T2 minus R T1 divided by del T. So, and this term, this is in terms of P. So, I can P, the graph will be not like this. So, the graph will change again for concentration versus time, the graph will be of this type, and this is T1, and this is a product at P time T1, and this is T2 T1, and this is product at time T2. So, here you see clearly the concentration at a higher time is higher than the concentration at lower time. So, you see clearly see, but here the concentration at higher time, here you see, is lower than the concentration in lower time. So, definitely there will be, the difference will come out to be negative, and the negative multiplied with the negative comes out to be positive. So, here negative only indicates the negative, the decrease of concentration, and finally it compensates the decrease in concentration, and the whole term comes out to be positive. So, in terms of reactant, so in terms of product, we can say this is PT2, PT1, this is always, there is positive is there. So, this represents the average rate. So, that means del T here, this square bracket I am using from the beginning. So, that represents the molar concentration. So, you have already all come across with this stands for, and T1 stands for, this is in fact T2. T2 means this is molar concentration reactant time T2, and this is molar concentration of reactant R in time T, and this is the difference. Difference means I can write it del T is equal to, this is T2 minus T1, and here also this is T2 minus T1. So, this is the mathematical expression for the average reaction rate. So, average reaction rate is the change in concentration over a finite period of time. So, now we shall switch over to the instantaneous rate. Now, we shall switch over to instantaneous reaction rate. So, that is like this RIN. So, what is it? At a given instant of time, that means a reaction is going on, we shall pick up at a particular instant at a particular point of time. So, where we need to know the reaction rate or the change in concentration that has been taken place in that particular point of time. So, this is in fact the extension of the average rate, and yes, I can write limit this del T approaches for the same reaction. I am dealing with the same hypothetical reaction. So, this is del R concentration by del T. So, the negative sign will be there. So, this will come out to minus d R concentration by dt, where del T approaches to 0. That means the time interval is extremely short. That means extremely short. That is, you can call it an infinitesimal time, in infinitesimal small time. So, this, and we can also find put it in a graphical form, and this is the fall of concentration of R. If I need to require, I need to calculate the instantaneous at this point of time. So, what I will do, I will draw a tangent here, I will draw a tangent. and this is the angle theta, tangent theta, and the slope of the tangent, this in fact the slope is equal to, I can take it tan theta if this is O and this point is B. So, this will be equal to OA by OB. So, that is your instantaneous rate. So, graphically we can get the instantaneous rate in this way. So, this is at a given, and similarly if we will take in terms of the product, formational product. So, we will get the same result, and this will be come out to be plus d by dt. So, that is also we can get in that way. So, that is we deal with two types of reaction rates, one is average rate, another is instantaneous rate. So, now I will give you a general reaction. I will give you a general reaction. Here you see, should I stop here? No. So, suppose I will give you a general reaction, like this, A, B, giving C moles of D and D moles of D. This is a general form reaction where, so here I can write the average rate like this, minus 1 by A minus 1 by B del B by del T is equal to plus 1 by C del T. So, if I will use the R infinite, so in terms of this del and this del, so this will be replaced by D. So, almost that will be same. So, I am not going to write it again. So, I will just writing one term minus 1A. So, dA by dt and go on like this, all will be same. So, this delta, this will be changed over to D. So, this is average rate. So, here there is a very important point is there. There is a very important point. So, here you see, so here there is a very important aspect here for problem solving basically. So, there are, you see, this whole term represents the rate of reaction, each whole term represents the rate of reaction or the average reaction rate. But this term, this represents what? This represents rate of disappearance of A. That means this is rate of disappearance of A. When it is multiplied by a factor 1 by A, then it represents the average rate. So, suppose I will take a general reaction. So, actually I will give you a problem here. So far we have learned the reaction rate and its types. So, average rate and instantaneous rates. So, now we shall switch over to the units of reaction rate. So, unit of reaction rate, it is very simple. So, once you know the mathematical formula for relating to that thing, so that is rate of reaction. So, you can evaluate the unit out of that. So, you know rate is equal to what is the change in concentration divided by time. So, here you must know what is the unit of the concentration and unit of time. So, that will give you the unit of the reaction rate. So, you know concentration, I have already told you, this is in moles per liter and this is time, you can take time. So, the overall unit will come out to be mole liter inverse time inverse. So, you can put in a bracket. So, why I have written here time? Because according to the length of the reaction going on, so the time will vary. So, it may be in seconds, it may be in minutes, it may be in days, it may be in months, it may be in years. So, depending upon the speed of the reaction, if it is a very slow reaction, you can measure it in second inverse. So, the unit will be come out to be mole liter inverse second inverse. So, or similarly I can it will be year inverse and so on. So, this is the unit of, this is general unit of reaction rate. So, now for the better understanding of the reaction rate, let us work out a problem on it. Let us work out a problem. See, here it is in the screen. So, the problem says for a reaction 2A plus B giving 3C, the rate of formation of C is given here, and find the rate of reaction. Rate of formation of C is given. You have to very careful while solving a problem. So, what is the reaction here? The reaction is 2A plus B giving you 3C. So, first of all you will write down the rate expression here, rate. So, what is rate here? So, I can write it minus 1 by 2 dA by dt, 1 by, this is in fact dB by dt, and this is plus 1 by 3 dC by dt. So, what is given? So, given that the rate of formation of C, that is which part is given? So, this part is given, this part is given. And what you need to find out? The rate of reaction. Rate of reaction means the overall stands for the rate of reaction. Rate of reaction, and this is rate of formation of C. Then rate of formation of C. So, which one? This one. So now it is given. So, what is the value is 1.2 into 10 to the minus 4 mole liter inverse second. Here you see unit is very important. So, if you will multiply it by 1 by 3, so this will come out to be 0.4 into 10 to the minus 4, and it will come out to be 4 into 10 to the minus 5 mole inverse liter inverse mole liter inverse second inverse. So, this is the answer, this is the answer, this is the answer. So, usually with the students what we do, so looking at a problem we get, so is a problem, how can you solve it? So, when you are solving a problem, you must see what are the data given, what data it is given. Next utilize your brain to the what equation we are going to solve here, and then and unit is also one important aspect. So, we will come in other problems where units plays a vital role. So, this is how we can solve a problem. So, I have already told the whole thing represents the rate of reaction, but this is the rate of disappearance or the rate of appearance or rate of formation or rate of decomposition, whatever may be. So, next another problem is also there. So, rate of formation of nitric oxide is given in that reaction, and so it has been asked for the rate of disappearance of O2. So, the equation is 4 ammonia combining with 5 oxygen giving you 4 NO 6 water, 4 nitric oxide and 6 water. So, in this problem you see there are only 2 parameters we have to focus. So, one is on nitric oxide, one on oxygen. So, these two things, nitric oxide and oxygen. So, rate in terms of these two, one will be minus 1 by 5 dO2 by dt, and another will be plus 1 by 4 dNO by dt. So, you see the rate of formation of nitric oxide is given, means this part is given, you see, and it is asked this one, this is asked, this one. We have to find out this, very simple now. So, what will this? This implies what? dO2 by dt will be come out to be 5 by 4 into that value is given, the value is 3.6 in 10 to the minus 3.6 in 10 to the minus 3, I think 3. So, now I can solve it. This will be 4, this will come out to be 0.9, and this multiplied with 4.5 in 10 to the minus 3 mole liter inverse second inverse. So, this is how we can solve problems on the reaction rates. So, they will be in competitive exams also will be asked questions like this. So, where these are very simple problems. So, you have to only have the ideas or the clear concept about the things. So, in the next we shall go in details about the chapter, the next learning aspect, that is the factors influencing the reaction rate. So, we shall start with the number 1, that is the nature of reactant. So, what do we mean by the nature of reactant? In fact, when a reaction progresses, what happens? So, the bonds existing in the reactants, they are broken, and the bonds in the products, they are being formed. So, the reaction will be faster or slower, it depends on the nature of intermolecular forces or the bonds that is going to be broken and going to be formed. So, that is why, so the nature of reactants, suppose I will take the three fuels. So, one I will take suppose coal, so another will be suppose petrol, and I will take LPG. So, if somebody will ask you, so what will be the order of combustion of these three fuel? You know, combustion is also a chemical process or a chemical reaction. So, where fuel combines with the fuel molecules combine with oxygen and gives rise to a product and energy. So, in that case, you will find that coal will burn slower, or in fact, it is the slowest, it will burn slowest, and petrol little bit faster, and this is the fastest, petrol. So, this is order. So, this is depending upon the reactant. So, if a strong bond in the reactant is going to be broken, naturally that reaction, the rate of reaction is going to be less. That means, the reaction will be slower. So, next is your concentration of reactants. So, here I have been shown to you the nature of chemical bonds involved that decide the rate of reaction, that is making and breaking of bonds. So, next is concentration of reactant is very important. So, here the three things are there: rate expression and rate law. So, the knowledge of these three things, so we can better know about the effect of concentration on the reaction rate or how fast a reaction occurs. So, already you know what is rate. So, rate means the production, the rate of formation of product, or the rate of disappearance of reactants. So, in that way we can know the rate. So, there is another term. So, we will that is known as rate expression. So, there is a term called rate expression. What is that thing? What is rate expression? So, you all know the law of mass action. So, the law of mass action says that the rate at which a chemical reaction proceeds is proportional to the product of the molar concentrations of the reactants, and each raised to the power equals to the stoichiometric coefficients of the reactants in the balanced equation. Suppose I will take a reaction like this, A plus B giving rise to products. If I will apply law of mass action, so rate, it says this is proportional to, in fact, A concentration A, B concentration, and it will come out to a K, A concentration A, B concentration B. So, this expression is called the rate expression. This is called an rate expression. Here these powers of the constant powers, they are the exponents, they are been obtained from the balanced chemical equation. So, this is a rate expression. It shows also the variation of reaction rate with terms of concentration. So far we know the rate expression that comes from the balanced chemical equation. So, where the power raised by the concentration terms comes from the stoichiometry of the balanced equation. So, that was the rate expression. Now, we shall go to the rate law or rate equation. So, this is in fact more important. This is rate law, or we call it rate equation. So, let us take the same hypothetical reaction, A moles of A reacting with B moles of B giving some products. We are least concerned with the products. So, because we can ascertain the rate either from the reactant side or the product side. So, here, so the rate, so expression will be like this. So, here k a to the power alpha b to the power beta. So, here I have not chosen this a from the coefficients of a, the small a, not chosen. I have altogether different coefficients alpha and beta, and here these two coefficients alpha and beta, these are experimentally determined, these are experimentally known or determined, experimentally. So, since these two terms are experimentally known, so the whole equation is experimentally known. So, these are called the reaction order. These terms alpha and beta called the reaction order, and alpha is the reaction order with respect to A, and beta is the reaction order with respect to the reactant B, and the overall reaction order is the sum of these two, alpha plus beta. This is the overall reaction order, this is alpha plus beta. So, here these are experimental known quantity, and this equation this is experimentally determined. So, this is called the rate law or the rate equation. So, how can you define a rate law or rate equation? That the equation representing the variation of rate of reaction in terms of the molar concentration of the reactants, and the reactant terms raised to the power certain powers, so which may or may not be equal to the stoichiometric coefficients of the reactants in the balanced equation. So, this is the balanced equation. So, these are here A and B, and this alpha and beta. So, they may or may not be equal. So, this alpha plus beta, which is called the reaction order. So, this may or may not be equal to the A plus B, this may or may not be, and this is called the overall order, and alpha is the order with respect to the reactant A, and this is the B. And here the one more term is there, this K, this is very significant here. This is called the rate constant, we can call it rate constant or velocity constant, or we may call it specific reaction rate. So, usually very frequently we use this term rate constant, and this is a big term. So, therefore, velocity constant also frequently used. So, this is good. Now, let us define this what is this velocity rate constant. This is very important terminology used in chemical kinetics. So, that is rate constant. So, we can also define this term directly from this equation. So, I have already told you. So, once the all other parameters are known, so this is a new parameter here. So, you can define it in this term. So, if concentration A and B are taken to be 1 molar, then rate will be equal to how much? K 1 to the power alpha, 1 to the power and beta, and this ultimately this will be equal to K, the rate constant. So, now we can define rate constant. So, rate constant is equal to the rate of reaction when the molar concentration of the reacting species are unit. Very simple. This is the definition. The molar concentrations are unit. So, this is rate becomes equal to the rate constant. So, now I will come to the unit of the rate constant. This is also a very important aspect of the chapter. Unit of K. K stands for the rate constant or velocity constant or specific reaction. Why we use the term specific here? Specific stands for the rate of reaction when the molar concentration of the reactants are specific. What is that specific value? 1 molar. So, therefore, the term specific reaction rate is also been used. So, again, so we can calculate this rate. So, from that mathematical expression K, suppose this is A to the power alpha and B to the power beta. So, unit, so So, this implies your K will be equal to rate divided by these three things, alpha, b to the power beta. So, rate is its unit is mole liter inverse. So, let us say second inverse. And what is this? This is mole liter inverse to the alpha, and this is mole liter inverse to the beta. So, they will be added off, the powers will be added off. So, this will be alpha plus beta. So, let us say this alpha plus beta is equal to n. So, if this will be if I will take n, so this will come out to be mole liter inverse to 1 minus n second inverse, where n is equal to alpha plus beta, that is the overall order. So, now this is the unit of the rate constant, mole liter inverse 1 minus n second inverse, or you can take time inverse. So, that represents the unit. So, now I will ask you a question. I will put a problem here again to know something about of this. So, suppose a question is there, if rate constant of a reaction, any reaction, is 175 into 10 to the power 1.71 into the minus 2 mole minus 2 liter square second inverse, then what should be the reaction order? What should be the reaction order? It is a very, very tricky question here, you see. So, nothing, no data in terms of number is there, and number is assigned with a unit. So, and nothing is there, nothing more. So, you cannot use any equation to find out the order of the reaction, or reaction order, or whatever. So, here we shall use this unit to know the order. So, you know the general unit is of this is 1 minus n second inverse. So, what is given? This is given mole liter inverse to the power. So, you can take it as minus 2 second inverse. This is given, that means this is equal to this, is not it? So, now I can equate this minus 1 with minus 2. 1 minus n is equal to minus 2. So, this implies n is equal to 1 plus 2, that is 3. That is 3. That means the order of reaction is 3. So, it is a, so that means the reaction in the question that is been asked the order. So, it is a third order reaction, I can call it a third order reaction. You will be asked multiple questions on this also. So, given the rate constant is given this, and which of the following is correct regarding the order of the reaction. So, you can compute from the unit itself the order of reaction to be 3. So, this is the question. So, I think you all got it. So, this is an expanded form of the unit, and we know the unit in this form. So, I converted in this and this form again, and I equate this minus 2 with this power of this, and I got the result. So, this is how the problems and questions asked in many competitive examinations and even in our council examinations. So, this is order, and if a reaction has order is 1, we call it a first order reaction, we call it a first. If it is 2, we call it second order, if it is 3, and third order. So, now if I will in brief, I will tell you what are the main features of the reaction order. So, order may be 0, maybe whole numbers like 1, 2, 3, whole numbers, even fraction, and even negative. 4 things. Reaction order may be 0, maybe whole numbers, maybe fractions, maybe even negative, and it is an experimentally determined quantity. Order is an experimentally determined quantity. Number 2, and it throws light or gives idea about the path followed by the reaction. I will come in later. So, how the order gives idea about the paths or the mechanism of the reaction will come in later. So, this is the value, and I will give you an example where the order varies. So suppose I will take decomposition of ammonium nitrite upon heating. This will give rise to suppose N2 plus 2 water. So, this will be a first order reaction. So, order will be equal to 1, and suppose I will take ester plus alcohol. Any ester you take alcohol plus acid, you take any alcohol plus acid giving rise to ester plus water in presence of an acid. This here order comes out to be 2. And similarly, I will give you an example of fractional order CH3CHO giving rise to methane plus carbon monoxide. See, the order has found out to be 1.5. This is fractional, 3/2 fraction. So, these are all the experimentally determined quantity. So, this is all about the order of reaction. Now, I will go to another term used, that is molecularity. Molecularity. So, what is molecularity? Very simple again. Number of molecules we can say, or simply the number of reacting species. Number of reacting species. What are the reacting species? Maybe atoms, maybe molecules or ions. Reacting species taking part in an elementary reaction. Elementary reaction. In an elementary reaction, number of reacting species. This is in broadly we can say this is number of reacting species, atoms, molecules, ions taking part in an elementary reaction, that is called the order of molecularity of the reaction. So, again we can call it in this way also. So, molecularity is equal to, we can call molecularity is equal to number of species, reacting species in fact, simultaneously colliding to bring about a reaction. So, in this way also can molecularity. So, this is in fact a theoretical fact, this is a theoretical concept, because simply looking at a balanced chemical equation, so we can predict what should be the molecularity of a reaction. So, if the molecularity is 1, that means one molecule is taking part in a reaction, so it is a unimolecular. If it is 2, it is a bimolecular, it is a trimolecular, and so and so. And we can and it is always natural numbers. It cannot be a negative, and it cannot be non-zero. It cannot be fractional, so it cannot be 0. So, these are the aspects of molecularity. Then most important thing is here. So, while dealing with molecularity, so we must know two things. One is what is an elementary reaction? Elementary reaction or elementary step in a reaction. Elementary reaction. So, if a reaction is occurring in a single step, that means one step is there for the completion of reaction, is called an element. This is simply like one step reaction, elementary reaction. What is a complex reaction? What is a complex reaction? It is a multi-step reaction. Multi-step reaction. That means the reaction takes so many steps, more than one step or 2 or more steps for its completion. Already you have come across in organic chemistry. So, while dealing with SN1 reactions, so where the dissociation of the substrate, that is a tertiary alkyl halide, into a carbocation is a slow step reaction, and the combination of the carbocation with a nucleophile giving rise to the product is a fast reaction. So, this is that is a complex reaction. So, in this reaction you will find that it is very important, you will find that there will be a slow step and another is a faster step. In fact, the slowest step in a complex reaction is the rate determining step. It is very important. The slowest step is taken as the rate determining step. That means the reaction order comes out of the power of that rate law. So what we know that the slowest step in a multi-step reaction or in a complex reaction is taken as the rate determining step. And in multi-step reaction, in fact, only the slowest step is important for determining the reaction order or determining the rate. So from this we can conclude that molecularity is insignificant for multi-step reactions. It is meaningless in fact, and because the overall molecularity is differing from the single step molecularity. So molecularity, again I told you that it is an theoretical idea, whereas order is an experimental idea. So now I will come to one more point, that molecularity higher than 3 is rare. Why? It may be a question. Molecularity more than 3 is rare. So we can answer it in this way, that a 3-body collision is rare. That means I will come in later stage of this chapter, that is called collision theory of reaction rates. So according to that theory, the reacting molecules must collide among themselves to transform into products. So all the collisions that are going, they are not transforming into products. Only the effective collisions they give rise to the products. So what are the effective collisions? So effective collisions are those in which the molecules are properly oriented and they have minimum amount of energy called the threshold energy. They will overcome that energy, then they will collide and they will transform into products. So since 3 molecules, you see, suppose this is a molecule, this is a molecule. So once again, so I will draw it better way. This is a molecule. This is a molecule. So when they will collide in this way, so there will be chance of, suppose this is your A and this is A again, and this is B and B. So I will get the product AB plus AB. But if the collision is like this, so along this is AA and BB, and this will finally this is the thing. So here AA, AB, B will be there. So this is not a product, not a product. So here we get the product. So this is, you see, the 2-body collision are effective to bring about a reaction. So therefore molecularity more than 3 are rare. So this is all about this molecularity. So here I will again ask you a numerical. So I will ask you a numerical regarding the rate law or the order of reaction. So I have not made the slide. So you have to write for a reaction. The reaction is given like this. For reaction, suppose A plus B giving C plus D, the rate increases 8 times by doubling the concentration of both A and B, and rate increases 2 times by doubling the concentration of only B. So this is the data given, and the question is find the, or write down the rate law. Write down the rate law or find the rate law. What will be the rate law? So this is the question. So, so rate law means you have to express it in this way. So, rate, that means the question rate is equal to k alpha b to the power beta. So, this is, let us say, question number 1. So, if I can solve this problem for alpha and beta, so I can write the rate law or rate equation. So, what I will do here, so you see, so rate in place of rate I will write r, it will be better r. So, it is 8 r, this will be 8 r if a doubles and b doubles, both doubles. So, in that way this will be k 2a to the power alpha and this is 2b to the power beta, and this will come out to be k 2 to the power alpha plus beta a to the alpha b to the beta. This is, let us say, equation number 2. Equation number 2. Then there is equation number 3. So, this will be 2r. This will be k a concentration alpha and 2b concentration beta. So, here what the second part says? Second part says rate increases 2 times by doubling the concentration of only b. So, I have doubled the concentration of b and the rate becomes twice here, you see, and here both are doubled and the rate becomes 8 times. So, this will come out to be k 2 to the power beta a to the alpha and b to the power. This is equation number 3. So, now we are having 3 equations and 2 unknowns. This is the usually case. So, these alpha beta are unknown. So, we can very easily solve this and get the values of alpha and beta, and for which we can write down the rate expression. Suppose I will divide 2 by 1, equation 2 divided by equation 1. So, this will implies what? This will give 8 equal to this will be cancelled, this will cancel, k will be cancelled, this will come out to 2 to the power alpha beta. So, this implies 2 to the 3 is equal to 2 to the power alpha beta, and this implies your alpha plus beta is equal to 3. This is one. And again, if I will divide this 3 by 1, equation 3 by equation 1. So, what will give? So, 3, this will be 2 equal to, and this will be cancelled, this k will be cancelled, this will come out to be 2 to the beta. So, this implies your beta is equal to 1. If beta is equal to 1, then alpha will automatically 2, because the sum, the overall rate, sorry, the overall order is 3. So, the order with respect to your the reactant A is 2 and order with respect to the reactant B is 1. So, now I can put these values in equation 1. So, this will be R k a to the power 2 and only B 1. So, this is the expression, this is the rate law, this is the rate law, and this is the overall order, this is the overall order. So, the question may ask what is the overall order, the question will be like that, and finally the question will ask that what is the final order. Okay. So, this is all about the molecularity and order of reaction. So, we solved the problems for better understanding of these 2 terms, and now we shall switch over to the integrated rate laws or the integrated rate equations. So, where the rate law will be integrated to get the relationship between the concentration concentration in a given time. So, you can calculate from these rate laws or rate equations, integrated forms. So, then the next slide will be your integrated rate laws. So, what these give? So, they give the concentration of reactants in a given time, or how far the reaction goes, and we shall start it with a zero order reaction. So, in today's class we learned the reaction rate, the types of reaction rates, molecular in order, and all these related numericals we solved it, and in the next class we shall start the integrated rate laws. Thank you.